I do like passing the iPad around, and we'll come back to that. But so to finish up this part, oops, let's look at the question first. Does this seem right where we need to start? So in your notes, and actually one of the problems that you did to hand in today, you looked at the combustion of a hydrocarbon without any oxygen, and you had to come up with the relative numbers of moles. So this is another version of that, where now you also have oxygen in the thing that you're burning. So I think what I'll do is to kind of show you stepwise, because I was looking at your homework. That was why I was a little bit delayed. I went ahead and kind of streamlined hints for your homework. But in working this sort of problem, you can kind of think of it this way. Your first step is like you do it without oxygen. Basically, you're going to use the what we were using, the CO2, right, to get to moles. I'm going to just put it like this way. Use CO2, moles of carbon, right? And we use H2O to get to what? Moles of H, exactly. Now this is a little bit different, and you're going to see me on my builds here. We have to do an extra step. We need to get to the mass of oxygen. We need to get to the mass of this. So actually, we're going to take these moles of carbon and hydrogen, we're going to convert them back to grams, and then we're going to subtract those grams from the initial mass that was given, which in this case looks like it was the 0.236. So, in other words, let's see. I know it sounds like you're going backwards. It feels like it. Basically, you're going to use those moles of carbon you got to get to grams of carbon. And similarly, use the moles of hydrogen you got to get to grams of hydrogen. Like I said, it seems like you're going backwards. And then finally, you're ready to get to the mass of oxygen by difference. I'll just kind of summarize it that way. Because now you have the grams of carbon, the grams of hydrogen, and of course the compound is the grams of carbon, hydrogen, and oxygen. And then I guess just to finish that thought, and we'll do this, is once you have the mass of oxygen, you can get to moles of oxygen. I'll put moles of oxygen from step 3. So that's kind of what we have going on. So it's going to be very similar to what we did yesterday, or 2 days ago. So getting the moles of carbon from our mass of CO2, we start with the mass of the CO2, and what you guys did the other day was to use the molar mass next, at 44.01 grams per mole. That's the flipped version of the molar mass of CO2. That will give you moles of CO2, and then how do we get moles of carbon? Stoichiometry, exactly. 1 mole of carbon over 1 mole of CO2, exactly. And we're done. Rounding it to 3 significant figures, the moles of CO2 then that we're going to be using is that 0.00957 moles. Do I say moles of CO2? I'm sorry. Moles of carbon that we're going to be using. Moles of carbon in the thing that you burned. All right, we're going to do a similar thing with water and hydrogen. So the mass of water was 0.172 grams. What's the molar mass of water? 18.02 grams per mole, exactly. So we use the flipped version of the molar mass of water to get to moles of H2O. And so what's the relationship between moles of hydrogen atoms to moles of water? 2 to 1, very good. And that's what we do next. Perfect. So we're going to round according to 3 significant figures because that's what the mass of our water was. So the moles of hydrogen atoms in the thing we burned was 0.0191. So this is the next, so this was just like we did before. Now the next step, like I said, it feels like we're going backwards, okay? But we need to use the moles we just found to say what the mass of the carbon and hydrogen was in the thing that we burned. So if we start with the moles of carbon that we came up with, that 0.00957, let's see, do you guys buy this, that we can just look at the periodic table for the decimal number for carbon, the molar mass for regular carbon? That's 12.01. Of course, we're going to use the unflipped version, 12.01 grams of carbon per 1 mole of carbon. And then we're done. That's the, okay. Rounding wise, it looks like 3 significant figures. Yeah. So 0.115 grams of carbon was the mass of carbon in that thing we burned. Back, the last slide you have that we came up with the moles of hydrogen was 0.0191. What's the decimal number for hydrogen? 1.008. Yep, 1.008. Very good. So we're going to use the molar mass of hydrogen, 1.008 gram per 1 mole. And we're done. That'll give us the grams of hydrogen. So 3 sig figs. Okay, so 0.0192 grams of hydrogen. Phew. Now don't forget those moles, though. We're going to come back and use these 2 moles here in a minute, okay? It's funny because we kind of went backwards, but we're going to use these here in a minute. So now we can go ahead and by difference get the mass of the oxygen. So in the problem, it said that the mass of the sample was 0.236 grams. 0.236 grams. And I probably, doing this another time, I would have put that mass under the CHY0Z, okay, the thing that was being burned. And then we came up with the mass of carbon, 0.115. We came up with the mass of hydrogen, 0.0192. We don't do a lot of subtraction in chemistry, but we are here, so we round according to decimals, not significant figures. All right. So we need the third relative moles, and that being of the element oxygen. So we're going to take that mass, put it over 1, and we're going to use the decimal number for oxygen. What's the decimal number for oxygen? Isn't that a cool number? 16.00. Yep. So we're going to use the flipped version, though, right? Because we want to be left with moles. 1 mole of oxygen over 16.00 grams. Round to 3 sig figs. And voila, we have our Z. That's the relative number of moles of oxygen in the stuff we burned. So, and this just kind of cautions you, those relative moles we're going to deal with, we need to normalize them back to whole numbers. We need to get them back to integers. Because those relative number of moles just kind of randomly came that the mass of the thing that was burned happened to be 0.236 grams. So I'm going to go ahead and you know how I usually set up a little table here. Element. I got 3 elements. Carbon, hydrogen, oxygen. Number of moles that we got on the last few slides. I've jotted them down because I wouldn't remember. Carbon looks like 00957. Hydrogen 0191. And the last one we got, oxygen, is in the least amount, 00636. So I'm after to try to get whole numbers, and it really kind of works pretty good if you make a column here, and we're going to divide by the smallest number. So what's the smallest number there? Yeah, it is oxygen. So we're going to divide everything by 0.00636. And I went ahead and did that at my desk. And for the relative moles of carbon then, I got 1.50. Relative moles of hydrogen came into line with an integer, 3.00. And of course, if you divide 0.00636 by 0.00636, you get 1. So this is one where we're not ready to go ahead and give the empirical formula yet. We're going to go ahead and clean things up, you know, recognize that how can we get rid of the 0.5? Multiply by 2. Mm-hmm. Yep. If we multiply everything by 2, then that gives us 3.00, 6.00, and 2.00. And then we're ready to go ahead and give the formula. So what, it's C3H6. I love the end part of problems. O2. Okay, seem reasonable? So an alternate way to do it and get the same answer is just to kind of take a pair of them, first the carbon and oxygen, okay, and then the hydrogen and oxygen. And the reason you're picking on oxygen is oxygen, again, is in the least amount. So what you'd see right away with carbon and oxygen is you kind of got an issue with halvesies there. So we can clean that up, of course. 1.5 to 1 is the same thing as 3 to 2. And then looking at hydrogen and oxygen, we get right away a 3 to 1. Okay, so this is where, in my own mind, it would get confusing, but we know we have to scale up the oxygen, so we also scale up the hydrogen. Relative to 2, we have 6. Relative to 2, we have 3. Okay, so you get the same results. Cool. Dun, dun, dun. So in your homework, it's kind of neat, and I'm glad I took a look at it so we can look at it. You know, it is a long weekend if you're stuck. To apply this technique to other things that are combusting and have other elements in there that end up as combined with oxygen on the product side. So you guys already did this one. Okay, so these 3 will be due on Monday. I do think we'll take a look at them right quick right now. Any questions? If I can figure out how to do that. Oh my goodness. Oh yeah, there it is. So funny. There it is. Okay, so this is the hints for the one that was due today. Okay. So I'm going to kind of clean it up here. Oops. Really? All right. Let's do that. All right, so if you read this, you see that, again, it has oxygen in it, and there are 3 parts to it. The part B, actually, I'm going to knock out part B first. It's what we've just been working on. It gives the mass of the thing you're burning, and part B says what is the empirical formula of it. Okay, so the thing that we're burning has oxygen in it. Okay, and the delta means adding heat. These will be available through Twitter. So the mass is given, the initial mass of the thing that was burned, and of course the mass of the carbon dioxide in the water was also given. So like I said, I would focus on B first. So what we just did was we got the moles of hydrogen from the mass of water, we got the moles of carbon from the mass of CO2. Step number 2, I have here what we just did. We kind of backtrack and get the mass of the hydrogen from the moles of the hydrogen and the mass of the carbon from the moles of the carbon. And then what we just did finally is to knock out the mass of the oxygen by difference. Once we have that mass, we can go ahead and get to the moles of oxygen. And that last step is to kind of clean it up, to get the relative moles in whole numbers. I would do that first. There's 3 parts. Once I had the empirical formula, I would then turn to, you go either way, but I like A, to get the mass percent, basically you're after the weight brought by the carbon, the percent brought by the carbon, the percent brought by the hydrogen, the mass percent brought by the oxygen. So I would go ahead and divide each of the mass of each element by the total mass of the empirical formula. Now, for that last one, and actually we talked about this in, I think it might have been part 2. Notice that we come up with the empirical formula. Okay, the molecular formula is kind of could be a multiple. The molecular formula is more complicated. So they went ahead and gave us the molecular mass, that 108.1. So we talked about how to do this one. Basically, you take that large molecular mass and you divide it by the mass of the repeating unit, or the mass of the empirical formula. And hopefully you get an integer. Okay, it'll either repeat twice or 3 times or 4 times. And if we just kind of call that x, then you're going to take that x times your empirical formula to scale it up to what your molecular formula is. So that's your hints for that one. The next one, oh good, it didn't go on for me. Okay, so this one is what was alluded to just a little bit ago. Just a little bit ago, it said we can use this technique if you're burning something that has other stuff in it. So carbon, hydrogen, sulfur. Notice you're like, dang, how the heck? And then you look over the product side and you're like, oh, that's okay. All the sulfur in the thing I'm burning is going to end up as sulfur in SO2. I'm cool with that. So basically, you're going to do kind of 3 little problems on the front end. So you're given the mass of what you started to burn and the mass of all the stuff you did burn. Notice, though, I just think this is kind of funny. We don't really, as far as I can tell, need to use this mass. Okay? So if you kind of break it up into parts, you can get the moles of the hydrogen, from the mass of the SO2. Okay, so we'll have 3 relative moles. And then my last step there is just to go ahead and normalize those relative moles to get them into integers. And remember, that's where I kind of make up the columns and I divide by the lowest number. Okay? The next one, I'm glad to, I'm thinking, you guys have it so lucky. All right, so this one, if you read it a few times, it looks like you need to kind of just do what we've been doing. But that's not the case. They give you the mass of the thing you're burning. They say it has oxygen in it, so we're thinking, oh, it's the more complicated problem. And now they say there's excess O2, and then they say what masses of these should we get? Okay, and I'm going to tell you this is just a regular stoichiometric calculation. We're going to go from grams of C4H10O, because they gave that to us. They gave us the empirical formula. We're going to go from grams of that to grams of CO2, grams of that to grams of H2O. That's what the question's asking for. The only catch, though, is you need to balance it first. And I've gone ahead and done that. So with a little bit of sweat, I came up with a set of coefficients of 1, 6, 4, and 5 to go ahead and balance it. Okay. So then, like I say, kind of finish out the hints here. It's just a regular stoichiometric calculation, going from the mass of that reactant to the mass of those products. Any questions? Yeah. So it's all good. Okay. On with dun dun dun. Thermodynamics. But if you're one of those that looks ahead and looks for the assignment slides and there is no assignment slide for part 1, unit 3. Good, bad, or otherwise. this subject's kind of tough, and I'm not saying that to psych anybody out. I think it would be tough for little kids even, because as we talk about energy, it's not really something you can say, oh, I got that energy. Really? You know, you can feel the energy if it's heat. You can see the energy if it's light. You can see things move, you know, if it's like momentum or something. But so that's kind of, we're looking at heat. We're looking at kind of what we call the transfer of heat. In general, when somebody talks about thermodynamics in engineering, they're talking about heat being transferred. So something's gaining heat or something's losing heat. A flow of heat. I told you our daughter's chemical engineering, and she does a lot with thermodynamics. Okay, so we need to make sure we're all on the same page with some terms. Energy, in general, is the ability or capability to do work. Whether you do the work or not is another thing, because there's potential energy and kinetic energy. But energy is the ability to do work and or transfer heat. So energy is the ability to do work or transfer heat. Now there's two, broadly speaking, types of energy, and you've probably seen these kind of in physical science before. I call them yin and yang. We can talk about energy as either being potential or stored energy, or energy is kinetic. Kinetic energy is associated with motion. Kinetic energy is energy kind of in motion, or in being spent. Potential energy, we could have potential energy because of our position, our condition, or composition, what we're made of. Some other terminology associated with thermodynamics or associated with energy is the calorie. There's two calories. There's two types of calories. Okay. So actually, as it turns out, the calorie is not the metric unit of energy. It's the joule. But starting with the calorie, it's kind of cool. And in Monday's lecture, I'll probably bring this up when we talk about specific heat. But calorie was defined if you have exactly 1 gram of H2O. I'm going to fill that with H2O. And it is exactly, no uncertainty, right? Yeah. But if you read the description, it's basically a little experiment. It says you are going to pump energy. Let me change my. You're going to pump that cube of water with energy. Okay, I'll put a question mark here. And it is going to go from a temperature, T is equal to 14.5 degrees Celsius to 15.5 degrees Celsius. It's a little experiment. The cool thing about us all using the same units is that we should be able to recreate this other places. Okay, so the energy required to make that happen is a calorie. So we'll be kind of coming back to that concept. Okay. So like I said, the metric unit for energy, though, is not the calorie, it's the joule. So I have a slide coming up here in a minute, and you're going to want to memorize the relationship between the metric joule and the English calorie. Okay. So you notice the word exactly? We know when somebody says that there's an exact relationship, that is an awesome thing. And this one was created by definition. So there's no uncertainty here when you do conversions between joules and calories. So one calorie is exactly equal to 4.184 joules. So there's a couple types of calories. There's the candy bar calorie, and then there's the thermodynamic calorie. Candy bar calorie is really called a dietary calorie. Okay. So the dietary calorie, the Snickers calorie, is a capital C and or, if you're using 3 letters for its abbreviation, a capital C-A-L. The thermodynamic calorie that we're going to be working with, the science calorie, well, I guess the other one is a science calorie too, but it's a lowercase c or a lowercase C-A-L. Okay. The relationship between them, and I always have to look, but you're probably going to memorize it, is 1,000. There's a factor of 1,000 between them. So the food calorie, capital C, it says, is equal to 1,000 thermodynamic calories. I wonder if they did that on purpose so people wouldn't feel so bad eating Snickers bars, you know, when you look at the back, to kind of scale them down. So I have a kind of a peach slide coming up here in a minute to kind of summarize all that stuff, the things you need to memorize. In the meantime, we said that by definition they set a joule to be a calorie is equal to exactly 4.184 joules. But a joule actually, as it turns out, you can do a little experiment too. And this is kind of fun. Let's kind of picture this. In the next slide, it says kinetic energy is 1/2 mv squared. So basically, here the mass is a 2 kilogram object, and it is moving with a speed of 1 meter per second. So if we go to say that KE, kinetic energy, is equal to 1/2 mv squared, do you see where that is equal to 1/2 times 2 kilograms times 1 meter per 1 second quantity squared. So kind of the 1/2 and the 2 cancel each other. So you end up with, when you solve that out, your units are going to be, kilograms, your units are going to be kilograms meter squared per second squared, and your unit is going to be 1. So 1 joule, in terms of breaking it down into kilograms meter squared second squared, is equal to 1. So it's kind of a neat little thing. These you don't have to memorize, but that's kind of how I got that. All right, these you do need to memorize. So you'll need them for problems on your homework and perhaps in the test. Okay, so commit to memory between the English calories and the metric joules, and also commit to memory, however you want to do that, between the thermodynamic calorie and the dietary calorie. So, all right. So again, still talking kind of vocabulary to make sure, again, that we're all on the same page. We talked about the kinetic molecular theory, the fact that all molecules and atoms and matter is in motion. And motion is associated with kinetic energy. So that's where we got the kinetic molecular theory. So objects have thermal energy, and I don't know which comes first, the chicken or the egg. The thermal energy is exhibited in its motion, or its motion is associated with its thermal energy. But one of the things I think would be good for you to get a grasp on this subject is to remember that as you cool something down, like if this is cooling down, actually it's going slower and slower. If I zap it with heat, it goes faster and faster and faster. Okay, so the thermal energy changes. Let's see if these play for us. I especially want this one right here. I'm not going to animate, but remember that with regard to, did I play that little girl who solid, liquid, or gas? Did I do that one for you? Not this semester. Basically, matter that's in a solid state has a little bit of kinetic energy, but not as much as if it's in its gaseous state. You can almost see it. Okay. This right here is going to show you that when things are hot, they will actually, their kinetic energy carry them so that they, I think of it as encroach on their fellow cooler neighbors. And they bump into them, and it's just a crazy sort of time. I hope it was already opening.
rapidly than those of the same substance with a lower temperature. If the two samples come in contact, a transfer of molecular momentum occurs from the rapidly moving molecules to the slower ones. In this way, thermal energy transfers from the hotter sample to the cooler one. When the two samples have similar rates of molecular motion, they have the same temperature.
So I wish I could give a copy of this to everybody and you could put it under your pillow, because honestly, when we talk about heat transfer, that's what's happening. And the more you can visualize stuff at the macroscopic level, the more successful you'll be. So, and that's part of what it's all about. Define success story. Okay. So I've talked about thermal energy and heat, and thermal energy and heat are synonyms. They're a type of energy, thermal energy and heat. They are totally synonyms. Temperature, not so much. Temperature basically is you're taking your little probe, okay, and you're sticking it in something, and you're trying to get a sense for the kinetic energy of it, or get a sense for the kinetic energy of it, but it's not the whole story. The one thing that temperature does do is it will tell you the direction that what will get, if you have two objects like we had a minute ago, where the hot and the cold, what the relative temperatures of them will do is to show you the direction that heat will flow. And if you think about warm objects having a lot of kinetic energy, okay, honestly, the heat is always going to flow from hot to cold. It's just the way it does. Thermal energy never goes from cold to hot. Okay, so we can use heat and thermal energy interchangeably. Temperature, like I said, although temperature is an indication of the amount of thermal energy an object has, it's not the whole story. And on Monday, we're going to have to kind of complete the story. How do you look at an object, take its temperature, and use that to say how much thermal energy it has? There's more to it, unfortunately. So we talked in Unit 1 about properties or characteristics, and we talked about kind of the yin and yang of intensive and extensive properties. We said intensive properties are independent of amount, and extensive properties do depend upon amount. And so kind of up here, and actually this is the example we're going to look at Monday. For instance, if I had water in two amounts, if I have water here in this is going to be a butch drawing, but this is supposed to be my bathtub. So it's got okay. So that's a tub. Okay, and I fill it up with water, and I'm going to make my water, I'm going to say T, that's temperature, is equal to, let's see, boiling Celsius, 100 Celsius. Let's go with 90 degrees Celsius. Now, I think that might be really hot. Okay, T is equal to 9 degrees Celsius. It's a tub. And then over here, this is going to be my little cup, not drawn to scale. Okay, I'm going to have a cup over here, and I'm going to say that the temperature there is also 90 degrees Celsius. So here's the deal. They have the same temperature. Okay, temperature is independent of whether it is a bathtub full or a cup full. But which one of them, which bodies of water has the most thermal energy? The tub. Why?
Because it depends on the amount of it, there's more of it.
That's right. The tub has more energy, exactly. So extensive depends on amount, and so thermal energy or heat, okay, depends on amount. Exactly. So your intuition would say more heat, and you would be right. I guess that's another thing when we're working these problems. Sometimes we struggle working thermal dynamic problems, but kind of use your common sense, and that helps too. So like I was saying, on Monday we'll be talking more about how amount adds on to temperature to ultimately finally tell the story of how much thermal energy an object has. So yeah, I'm hoping that to kind of set the stage for the study of thermodynamics, we're all kind of on the same page. If you have a box of, we'll make them gas particles, that this is hot, okay, and you have a box over here of gas particles, same number of gas particles, and this is cool. One thing I haven't done yet, but in my own mind, this is how it works. If I draw a line with the hot particles, kind of showing how much motion they have, I'm going to draw a big line. With regard to the cool particles, not so much. So when we talk about the relative hotness temperatures, the relative temperatures saying what direction thermal energy will flow, I guess to kind of finish that thought, we could picture opening a channel between these two. So that's my channel opening to the two. It's like a dog door. We open a little door here, open a little door here. And guess which one's going to race out of the cage? Yep, the hot ones. They're going to go down here, and we'll probably make that little channel shorter. They're going to bump into these, and bumping into these, they're going to lose some of their energy, and these guys are going to pick up energy. Okay, so it's a lose pickup, and it kind of goes, and they finally end up at the same temperature, don't they? That's kind of setting the stage for kind of working problems. So we need to talk about 3 temperature scales. The Fahrenheit temperature scale is the least important for us. Okay, that's the old English. Although for me, I need to know I need to know the outside temperature in Fahrenheit. I'm not good with Celsius. But if we kind of look as water is kind of a milestone, water will boil at 212 Fahrenheit and it will freeze at 32 Fahrenheit. That's assuming 1 atmosphere pressure. And you might be familiar with regard to water on the Celsius scale. Water will boil at 100 degrees Celsius and it will freeze at 0 degrees Celsius. So the Celsius scale is metric. So darn those English. I don't know how it works. So anything metric kind of rules the day in God. Kind of. So here we kind of have some things in perspective. We have the boiling water and the freezing water. Freezing water, boiling water, and you see the Celsius and the Fahrenheit temperature. We have a third scale drawn on here, and I bet you guys can see it. The third scale is with the symbol K, and actually that is the Kelvin scale. And that is also metric. So here's all the Kelvin temperatures. In astronomy, when we talk about how hot a star is or how hot a planet is, we'll kind of talk about it in units of Kelvin. It's also, like I said, also metric. But, so, like for instance, water freezes at 0 degrees Celsius, 32 degrees Fahrenheit, and 273 units on the Kelvin scale. That's the other thing, is if you're talking about temperature in terms of units of Kelvin, you don't say degrees, it's units for some reason. But on this is actually the significance of the Kelvin scale. The temperature of 0 Kelvin is referred to as absolute zero. You probably heard this before. And I have a slide telling you how this works, or the significance of this. Basically, if you were to start at a very cold day, 238 Kelvin, very cold day, okay, and then you get colder and you get colder, you get down to the boiling point of liquid nitrogen. So like nitrogen is a gas, but if you cool it down enough, the boiling point is also the liquefaction point. Okay, so 77 Kelvin, okay, it goes ahead and it goes from a gas to a liquid. Okay, cool it down even more, okay, 5 Kelvin, basically you get just a little bit of motion, okay, 3 Kelvin, okay, get the idea, okay, 0 Kelvin, and there's no motion. And one of the things I think about is actually that is a premise of matter in our universe. All matter has motion. There's no motion. So it's an unacceptable state, basically. Nothing can be as cold as absolute zero. Nothing can be as cold as 0 Kelvin. Makes you want to go out and do it, doesn't it? There are people that, it's been maybe a year and a half ago or so, where somebody said, I got something colder than 0 Kelvin. And then you don't have to look too far at the article, because sometimes articles just like, oh my gosh. You don't have to look too far to see that they did it with kind of statistics, kind of a bell curve, and they said, well, yeah, the distribution would say that some of them were colder than 0 Kelvin. So anyway, there you go. One of the things you won't need to do in here is this. Nurses might, because the whole Fahrenheit, Celsius, the whole English to metric, like that. You won't need to convert back and forth between these two. But it's hard, and I'm going to show you the little equation thing to use. The problem of going back and forth between these two scales is these two scales are what we call interval scales. Interval scales are great, okay, but they're not ratio level scales. So let me kind of say what I mean. So starting out from the crudest type of scale to the most sophisticated scale. There is a scale out there that basically has no numbers, okay, and no rank. So for instance, we could go in this room, go in any room, and you could say, we have blondes and we have brunettes. Okay? No ranking, no numbers. That's a nominal sort of measurement. We could go in and we could do the same thing. Okay, it could be a blonde joke here. Sorry, I better be careful. We could go do the same thing and imply a ranking, like blondes are the smartest. And then, of course, we have brunettes, and then we have, redheads. And we could go ahead and apply a ranking, okay, but still non-numeric data. Okay, that's still not as sophisticated. And then we go ahead and we have numerical data, okay, but there's no true zero. And let me use Celsius and Fahrenheit as an example. So the zero on the Fahrenheit scale, what does it mean? It means colder than freezing water, right? 0 Fahrenheit. But is there a negative Fahrenheit? There are negative 10, negative 30. Yeah, heavens. So the problem is the 0 doesn't mean anything. The units, they continue in intervals on both sides of 0. So you know where I'm going with this. If you look at the temperature scale for Kelvin, okay, can you go on the other side of, 0 Kelvin. Can you go on the other side of 0 Kelvin? No. 0 means something. Actually, it means, in that case, for temperature, it means the absence of thermal energy, absence of heat. But not so complicated. Length is another example. Does 0 really mean something? Because, like, if you have 1 inch, 1.5 inches, you got something. Okay, you have 3 inches, you got something. Let's go the other way. 1.5 inch, 1 inch, 0.5 inches. What if somebody says, and all matter occupies space, so all matter has a length, but it's possible that something else doesn't have a length. What if they said the length is equal to 0? Absence of length. The mass is equal to 0, absence of mass. Okay, those also are at this important interval sort of level of measuring things. Okay. Oh, sorry, they're at the ratio level. Dang it. So just to kind of clarify, over here at interval level, I'm going to go ahead and put Celsius and Fahrenheit, degrees Celsius, degrees Fahrenheit. And at the ratio, I'm going to put the Kelvin temperature scale, and I'm going to put let's see, what else I put? I put length and also mass. Okay. So a true 0 in the ratio level, not the interval level, really means something. What means anything anymore? The older you get, the more reflective you get. Okay. So what this actually is kind of an XY plot of the Celsius and the Fahrenheit temperature scale. Along the x-axis are Celsius temperatures, and along the y-axis is the corresponding Fahrenheit temperature scales. And you're familiar with plotting things and coming up with a straight line. And the equation for this straight line is given right up here, where we can use that, y is equal to mx plus b. Don't worry. But basically, I'm kind of coming up with developing a relationship to go back and forth between Fahrenheit and Celsius. Okay, so this is the thing you won't need to use this semester. I actually have the thing Google down here. You can ask Google to go back and forth between anything, including Fahrenheit and Celsius. But if you want to know, for instance, Fahrenheit, you plug in the Celsius temperature there. And if you want to know Celsius from Fahrenheit, you plug in the Fahrenheit temperature cell. Fahrenheit temperature there. And like this says, the numbers 32 and 1.8, there's no uncertainty associated with them. So like I said, you're not going to have to do these, but we could use the previous equation to go from 25 degrees Celsius to what its Fahrenheit temperature is, and 98.6 degrees Fahrenheit to what its Celsius temperature is. Oops, sorry. Okay. So again, the Kelvin temperature scale is the ratio, most sophisticated type of scale, where 0 really means something. It's metric. Yeah, it's metric. One of the things that probably said a minute ago is that since it's metric, I guess, 1 unit on the Celsius scale is lock and step with 1 unit on the Kelvin scale. So it is kind of nice. They're offset. So actually that leads me to one of the last things that you do need to memorize these. So it is my pleasure to go ahead and tell you, don't learn how to go back and forth between Celsius and Fahrenheit. Do learn how to go back and forth between Kelvin and Celsius. So the fact that they are lockstep, the same, okay, then that means we can just add the offset, which is 273.15 units. Okay? All right, so you'll have some chance to apply that. I think that's it. Have good weekends.